Okay, hi everyone. Welcome to another MLFL. This week, we're very excited to host Professor Rose Yu, who is an assistant professor at the University of California at San Diego. She was a postdoc fellow at the California Institute of Technology before joining UCSD. Her research focuses on advancing machine learning techniques for large-scale spatiotemporal data analysis with applications to sustainability, health, and physical sciences. She has won several awards in the past, including faculty research awards from Facebook, Google, Amazon, and Adobe, Best Paper Awards, the Best Dissertation Award at USC, and she was also nominated as one of the MIT Rising Stars in the ECS. So without further delay, I'll hand it over to Professor Yu. If anyone has any questions during the talk, feel free to raise your hand or drop a message in the chat. And you could also unmute yourself and ask the question. We'll also have like a Q&A session at the end of the talk. Okay, over to you, Professor Yu.
Oh, thank you so much for the invitation. It's really a great pleasure to talk here at the UMass Amherst, because this quarter I'm teaching a special topic class on deep reinforcement learning, which is something I'm very interested in. And I'm using a book written by some faculty here at UMass Amherst. So it's really a great pleasure to talk in your school. So I wanted to share some of the recent work about learning generalizable dynamics models with deep learning. And I direct the spatial temporal machine learning lab at UCSD, right? So some examples of spatial temporal machine learning can be seen as follows. Like one example is modeling the pandemic dynamics, and the number of cases is increasing. It's very non-stationary. So it's very hard to model the progression of the pandemic. The question is, well, can we develop somehow more flexible models and being able to generate scenarios and forecasts for policymakers? Another example is in climate science. We have data and simulations generated from different space and time. Right? This video shows the temperature variation for the past 50 years. We know climate models are very crude, and they're very slow to simulate at high resolution. So the question is, can we develop data-driven surrogate models that can be much more efficient and high fidelity to describe the climate phenomenon? Another example is in traffic, right? So in transportation, we have sensors collecting at different location and time. And the bubbles you see represent the accidents in the city of LA. Right, so this is a traffic flow. The kind of color map shows how the flow evolves over time. So again, in transportation, right, there's a lot of rigid models that describe drivers' behavior, which might not be very realistic. So the question is, can we leverage the data collected by huge amount of sensors and all the detectors to improve traffic modeling for planning purposes? So as you can see, the common pattern among these applications, right, from public health to climate science to transportation, the common theme is that the data contain very rich space and time information. So if we can exploit this rich spatial temporal information and develop machine learning models that can learn spatial temporal dynamics, then we'll be able to drive real-time decision-making in a lot of the science and engineering field. So that's the focus of our lab, spatial temporal machine learning. Today, I want to focus on the particular issue of dynamics learning, which is generalization. So just to give you a hint of what we mean by generalization, this is an example taken from one of our papers published at L4DC. So here we're looking at the forecasting setting for a toy model of forecasting sign functions. So in this case, we are given the past states, right, from 0 to 30, and we wanted to forecast the future states or future values of the sign function from 30 to 60. So this sequence, one sequence is one example. And the sign function is governed by some parameters. Let's call it theta. So in this case, theta includes the phase of the sign function and the magnitude of the sign function. So in the setup, what we did is that we draw samples from a particular parameter interval, right? So this parameter governs the dynamics of the system. And then theta-tr represents the training parameter regime that we sample from. And then in the left plot, basically, we draw samples from a training set and evaluate a learned model on a test set. And both dynamics parameters are of the same range. So we basically tested different type of deep sequence models. And it's not surprising that the sequence models can perfectly predict the future evolution of the sign function given the ground truth. However, if we slightly change the setup, right? In this case, we have parameter theta, let's say coming from the interval A and B, representing the phase parameter and the magnitude of the sign function. But during testing, we change how we sample the data, where now the parameter is sampled from a different interval, B and C. So in this case, there's dynamics change, right? But then it doesn't matter how we choose the deep learning architecture, but we tried a lot of different state-of-the-art deep sequence models like transformers, neural ODEs. None of them can work in this case. It's just because there is distributional shift in the dynamics itself. So this is the issue of generalization, because deep learning models for dynamics modeling cannot generalize naturally. So generalization is a fundamental challenge in dynamics learning. Or typically, when we talk about distribution shift or generalization issue, we're only talking about the changes in the value of the data set. But in our case, we not only need to do, actually the distribution of the data are quite similar. So they have similar ranges for the sign function from training to testing. It's actually the underlying parameter that govern the dynamics are changing from training to testing. So that's constitute a slightly different situation of distribution shift. And we know that deep learning struggles with changing dynamics, performance degrades with test distributional shift. So I want to emphasize this kind of shift is actually on the parameter that governs the data, not necessarily on the data distribution itself. Okay. So this is a fundamental challenge. How are we going to kind of resolve this kind of issue? So in the past few years, we've tried to look at this problem from a slightly different perspective, using the idea of symmetry. So because a lot of times when we deal with space-time data, this type of data are governed by physical systems, which pertain to certain physical laws. So the idea of symmetry is that even though the dynamics have changed from training to testing, the laws of physics do not change. So if we can somehow preserve the laws of physics in our deep learning model, then hopefully our model is able to generalize to different distributions of the dynamics. And Noether's theorem gives us this intricate relationship between symmetry and conservation laws. She says that for every symmetry, there is a corresponding conservation law. For example, translational symmetry will correspond to conservation of momentum. Time invariant symmetry will correspond to conservation of energy. So the high-level idea of building symmetry into deep dynamics model is that we want to use symmetry as an inductive bias to improve generalization, to reduce sample complexity, and most importantly, want to increase our trust in AI, because for scientists or engineers, if we can show that our model can preserve laws of physics, then they will have more trust in the predictions around model. So to use symmetry in the context of deep learning, we need to borrow some concepts from group theory. So as a starter, right, for those who are not familiar with group theory, a group is a set, G with a composition map to itself. So G compose G maps to G itself. And identity is an element in the set. And for every element in the set, there is a inverse element, G inverse. A familiar type of group is the rotation group in 2 dimensions, the SO2 group. So for the SO2 group, if we rotate this object by 60 degrees clockwise, there is an inverse operation, inverse transformation, G inverse, which rotates the object counterclockwise by 60 degrees. So with the group definition, we are ready to define what we mean by symmetry or invariance and equivariance. So the function is symmetric, is that if we have a function and a group G, when we apply this group transformation to the input of this function, it will not change the output of this function. In this case, we call this function is G invariant with respect to the group G. A more general definition of symmetry is equivariance, which means if we apply a transformation G to the input, it will automatically apply to the output of the function. In other words, f of g of x equals g of fx. So concretely, what does that mean? Let's consider this function to be the velocity field on the field x. So x is a field in 2 dimensions, and v is a scaling function. So scales up the velocity field by 2 in terms of magnitude. Let's consider the group as a rotation group in 2D. So the 2D representation for the SO2 group can be written as a 2 by 2 matrix with this type of elements. So it's an orthogonal matrix that rotates the object by theta degree. If a function is equivariant with respect to this group, that means if we apply the transformation first, which is in this case, we rotate the velocity field in 2 dimensions by 45 degrees, and then apply the scaling to stretch the velocity vectors by 2. It is the same as we first stretch the velocity field by 2, which applies the scaling operation, and then rotate it by 45 degrees. So going through the transformation on the bottom left corner is the same as going through the transformation on the top right corner. And if the function satisfies this condition, then we say this function is G equivariant. So when we talk about dynamics, naturally we need to talk about the equations that governs the dynamics, which lead to differential systems. So what do we mean a differential system has symmetry? Essentially, it's a solution of the differential system that has symmetry. So if we have, let's say, a system of differential operators, this represents first order, second order differential systems, the differential operators, which give us the velocity, acceleration, and etc. Then if phi is the solution of this differential system, D, then if we transform the solution, if it's still a solution, we say that this differential system D has a symmetry G with respect to G. Right? So that means if we transform the solution of a differential equation, if it's still the solution, then the symmetry belongs to the differential operator. So by this definition, we can derive different symmetries of familiar systems that we know. For instance, when we talk about the heat diffusion equation with the second order differential system, it satisfies space translation symmetry, time symmetry, and scaling, etc. Right. So another set of equation is Navier-Stokes equation, and Navier-Stokes equation is a governing equation of viscous fluids, which are extremely important in studying of fluids and turbulence in climate science, or even traffic flows. Right. For Navier-Stokes equation, it we can also show that it satisfies 7 different symmetries with corresponding parameters. Let's say, what's interesting about like Navier-Stokes equation is actually the parameter for scaling is not proportional. So when we scale the space by lambda, it actually scales the time by lambda squared. So there's a kind of asymmetric scaling behavior for Navier-Stokes equations. Okay, so our goal is to build symmetry into a deep learning architecture, right? And that leads to the set of deep learning models that are symmetry aware. And this line of research is called equivariant networks. So our goal is to basically define a neural network architecture F that is G equivariant. Because we know neural nets are universal functional approximators, but they may not be symmetry aware. So in general, if we want to design a functional approximator that is symmetry aware, we need to design the representations or the hidden layers in a specific way. So a function can be thought, a neural net can be thought as sequence of functional compositions. And then in between the layers, these are the representation of the group, right? Because a group transformation can be thought as implemented through a particular layer. And in our paper, we showed that, well, if it's actually quite easy to show if the maps between the layers are equivariant, then the entire network is equivariant. So even adding residual connections, such as in ResNet and other kind of dense net, right? If we're talking about on the linear actions, then adding skip tension does not affect the network's equivariance. So this gives us sort of the high-level recipe of defining equivariant network, which means we just need to guarantee that every layer is equivariant, and we can concatenate layers on top of each other that will give us equivariant networks. So there is this kind of intuition of implementing equivariant networks, which is through weight sharing. So we are all familiar with the architecture of convolutional neural networks. The reason convolutional neural networks are so powerful of learning image data is because of its translation invariance, because it assumes that the pixels actually have internal symmetry of translation invariance. So in CNNs, we have basically the filter in this orange block that are shared across different positions on this image. So we're looking at the two-dimensional grid, and then the weights within the orange blocks are very different, but across different orange blocks, they are shared. So because of this weight sharing scheme, in CNN architectures, it automatically enables translation invariance. So then this is, we're talking about the symmetry group of translation. But in general, if we want to design convolutional layers that are group equivariant with respect to general group G, then this convolutional layers kernel need to satisfy this condition called group invariance under conjugation, which means if we have a group kernel K of V, and when we apply the group transformation, so rho of G is a matrix representation of the group. So you can just think about it as a matrix. And then when we left multiply by this group representation, and then right multiply by the same group but possibly different representation. And if it's still the same, then we say this convolutional kernel satisfies group invariance under conjugation. And if that is true, this convolutional layer is G equivariant. So this gives us a recipe of designing convolutional layers that are G equivariant. Essentially, what we need to do is to construct the group representation for the corresponding group. And once we figure out this representation in matrices, then we're done. Right? Figure out the action maps, row in and row out for different groups. So any questions? Okay, great. So then as an example, right? So we're looking at the symmetry group for turbulence. This is done by my PhD student and postdoc and published at iClear. So the idea is that we wanted to develop deep learning surrogate models to speed up turbulence simulation at high resolution for climate science. There's a lot of work actually in deep learning to accelerate turbulence prediction. But the problem is that they often train their model on a specific dynamics, and then they cannot generalize to a different set of turbulence or distributional shift. So it significantly limits the existing deep surrogate models' applicability to real-world applications. And then we took this idea of symmetry and put that into the dynamics model to develop surrogate models for turbulence that are able to generalize within a group transformation. So for instance, we can look at the symmetry group of scaling. We know turbulence have symmetries in the scaling symmetry. For instance, the turbulence, the tiny turbulence that you see when we pour milk into the coffee has resemblance with the large turbulence in the ocean. So this kind of turbulence, or also called like self-similarity, right, in turbulence, points us to the scaling symmetry. So standard convolution enables translation symmetry, but they don't allow scaling symmetry. So in order to design convolutional layers that are scale equivariant, we must translate and scale the kernel across different resolutions, essentially. So at high level, what we did is that we need to construct kernels at different scale. So in this case, we're looking at the velocity field of turbulence, right? And then we can upscale the turbulence field by different ratio. And then we apply the convolutional kernel at different resolutions of the velocity field. So across different scales, the filters share the weights. So this is very similar to how convolutional filters share weights across different positions. Across scales, the weights are shared, but within each scale, the weights are fully trainable, right? So in this case, it boils down to designing this kernel T of K, T of lambda is the particular operator of scale lambda. And then when we apply this scaling kernel, we need to figure out the action map. And this turns out that the action map can be written as the scaling laws of the Navier-Stokes equation. So this is scaling space by lambda and scale the time by lambda squared. So when we figure out the T of lambda, right, according to the Navier-Stokes equation, then what we all need to do is to learn the weights, W, P of Q, for any positions on this velocity field. And this is how we design scale equivariant neural networks. In our paper, we also looked at 7 different symmetries for Navier-Stokes equations and derived a similar type of action maps. Okay, then let me show you the kind of performance of our model, right? So what you can see is that, if we're looking at the ocean current prediction, right? So in this experiment, what we did is we're training our model on a particular set of scales, but we're testing our model on data of completely different scales by upscaling the data with respect to different ratio, 1 over lambda. So we compared our model with a non-equivariant counterpart, ResNet, for forecasting ocean occurrence velocity. So it's not surprising that when we look at the non-equivariant models, because it cannot generalize under distributional shift, so the prediction error in terms of RMSE will explode when we upscale the data by different ratio. So the error becomes very high when we have very different data distribution in terms of scale. But for equivariant models in blue, you can see that the performance is very robust because the model can automatically detect the transformation in the data and then apply this kind of transformation to its predictions. So the right-hand side shows a physical quantity that is very important in climate science or turbulence modeling called energy spectrum error. So this is looking at how the energy decay appears in turbulence. And the error, the lower is better, right? So again, we can see that equivariant models allows us to generate turbulence prediction that have consistent physical characteristics with different upscaling ratio in the test set. But the non-equivariant model will have very bad performance in this case. So then this shows that our equivariant models does allow us to build generalizable models for a group of transformation, right? This is assuming we know the perfect transformation from training to testing. But in real world, we might not have that. So then that's what we looked at in the next one, which is.
So Professor Yu, we have a question from
Oh,
Professor
okay.
Moss. Yeah.
Yes, thank you. Just briefly, is this scaling for separate problems, or can there be within one problem portions that are working at different scales?
Right. Thank you for the question. So this experiment is for the same problem, which means that we're upscale the velocity field, which means there are two types of scales. One is like scaling in terms of the velocity field itself, right? By terms of scaling the velocity vectors. The other scale is in terms of the resolution. So we call it like physical scale of the turbulence. The other one is the actual discretized grid. So you can think of different resolution of the video in some sense, but still they're on the same system of the turbulence.
Okay, thank you.
Great, sure. So, okay, I want to briefly talk about this real world example of symmetry or equivariant networks for traffic flow forecasting, right? We know that, traffics can be seen as many particle systems, but it's more complicated than fluids because we not only need to model the dynamics underneath the traffic, we also need to take care of complex human psychology in driving. So this is done by my grad students, Leo, and postdoc Robin, and also published iClear. This idea of modeling traffic flow built on the key insights that many traffic dynamics resembles driven many particle systems. So there is actually implicit rotation symmetry in vehicle dynamics. Because when we know how to turn right in the United States, and tomorrow if we move to Australia, we still need to know how to turn right because there is intrinsic rotation symmetry that built in our decision-making, our system, I think. So in order to build models that can be successful at predicting traffic, this model should distinguish left from right turns and give consistent predictions when the intersections are rotated with different orientation as shown in the top picture. So we expect models to generate consistent predictions when we rotate the intersections by 90 degrees, for instance. So then we create the instantiation of the equivariant networks, but for the SO2 rotation group. The difficulty of the SO2 group is that it's continuous group. So there has been some research in equivariant networks for the rotation group based on the spherical harmonics. So the idea of spherical harmonics, you basically need to compute the Fourier coefficients of the decomposition, which is quite expensive computationally. Instead, in this paper, we propose a much simpler scheme to implement SO2 equivariance through this idea called orbit stabilizer representation. So we're looking at the particles or the position of cars in the polar coordinate. So in this case, we're focusing on the particular car. Imagine we have one car in the middle of this polar coordinate, and we're going to look at the cars around the centering vehicle and then discretize the space according to the polar coordinate. So because we want to implement the weight sharing scheme in this polar coordinate, so similarly, we can allow the weights to be shared along the orbit, right, of this polar coordinate, but the weights inside each of the slices, the angular component, to be fully trainable. So the weights are shared along the orbit, and that's for the continuous SO2 group. And in the middle, which is this singularity of the SO2 group, we have to be careful because this is the stabilizer of the system, or the bullseye. And to avoid the singularity situation, we need to constrain the weights for this particular position to satisfy a circular rule. So it's a circular matrix. Okay, then.
Just a quick comment. For Australia,
yes.
Wouldn't it be a reflection symmetry?
I said it depends on your reference frame. But that's a good point. I should change my example. Thank you. So okay, so then what we ended up with is a kernel that can be geometrically interpreted as a torus, right? Because our features is on a circle, and then because we're looking at, if we're looking at, you know, the kernel over two circles, right? It's a circle outer times another circle. So then the joint space of two circles is essentially a torus. So when we cut this open, the torus, we can see that the corresponding weights on this torus is exactly mapped to this polar coordinate. And the weights are shared along the orbit, but in the center, there is a circular matrix. So we can apply echo to, you know, traffic forecasting. In this case, we're looking at positions of cars. And then we want to forecast the future position of multiple cars at the same time, given their past positions. So the red dot is the agent, the autonomous car, like the autonomous vehicle that we're tracking. The blue cars represent other agents, such as the bicycles, pedestrians, and etc. So we use a type of encoder and decoder framework, right, to model the dynamics of traffic. In this case, we are encoding the map information and the multi-agent interactions by looking at the close neighborhoods of the agents, and then we're looking at the single agent dynamics. So we use separate continuous convolution, like our model, to encode the three modality of the data, and then we concatenate the hidden states of the output from all this continuous convolution. And then this module encodes the past history of the agent states. And then we're going to use a decoder to decode the future positions of the cars. Again, we're using continuous convolution and repeat many layers to generate prediction. So in this case, we're actually predicting the position difference delta x and add it back to the previous position to generate future positions. And for both encoder and decoder, we use our own proposed continuous convolution. So then we can look at the performance of different models on real-world data set. And these are two benchmark data sets in autonomous driving. One is autonomous driving, and the other one is pedestrian trajectory forecasting, Trajectory-Net. So we look at some baselines such as constant velocity, LSTM. Our major competitor is continuous convolution, and that's the non-equivariant counterpart of our model. And our model is called ECHO. We looked at two variations of our model, the row one representation and the regular representation. So we can see that when we look at the average distance error and the distance error at 1 to 3 seconds, our model has very accurate predictions compared with baselines. But that's not the most important aspect. We want to highlight how symmetry can help model to reduce the number of parameters. So when we look at the non-equivariant and equivariant version of the model, we can see that using symmetry as inductive bias, we can achieve 95% parameter reduction, which is important in embedded systems for autonomous driving, right, where number of parameters matters in a very small chip. And we also looked at how sample complexity can be affected by equivariance. So then this is the model that with performance we saw when we look at the validation error for distance error at 3 seconds. When we compare the non-equivariant model versus equivariant model, ECHO, we can see that equivariant model leads to 80% of data reduction. It only requires 20% of data to reach the similar performance in the validation set, and therefore it can generalize to real-world dynamics in traffic and compared to the non-equivariant counterpart. So this essentially shows that incorporating symmetry as an inductive bias can not only improve generalization, but also can reduce sample complexity and parameter complexity in the model. Okay, so that's the second example. And then you might ask that, well, a lot of times that we're talking about, so far we're talking about symmetries in the space of data. For example, in turbulence data, we're looking at different symmetries of the turbulence velocity field. And in the traffic example, we're looking at the rotation symmetry of the positions of cars. But in a lot of times, the symmetry might not be explicit, but in a hidden state that we do not know. So then how can we incorporate symmetry in a hidden representation of the dynamics? And that's the third example that I want to talk about, which is a recent paper that we published called Meta-Learning Dynamics Forecasting, where in this case, we do not assume the generalization only happens within the group transformation, but we allow different systems to vary from training to testing. And this is work done by my PhD students and postdoc. And in this case, we wanted to look at ocean currents again, but for completely different type of ocean currents, right? So let's say consider this example of turbulence. There are two types of fluid flow. The top one is a very static turbulent flow, right? So we are given a past states of the turbulence. We want to future the forecast, the future states of the turbulence. But then this is only happens during the training. But for testing, we're going to look at systems of completely different characteristics. So in this case, we're looking at a much more turbulent fluid flow. And given its past, how can we forecast its future? So the goal of this particular example is to develop models that can generalize your flows with very different buoyant forces, right? Because when we have different forces, it will lead to different turbulent behavior. The key insights that we have in this paper is that we notice similar dynamical systems, right? So even though there are different problems, they belong to the same set of dynamical systems. And similar dynamical systems share time invariant hidden features, because even though the velocity fields are changing over time, the characteristics, the features of buoyant forces are not changing. So this is a type of time invariant hidden features that we wanted to infer by observing the velocity field in the input. So our model ended up being a latent variable model that can exploit the symmetry in the hidden features, and that's lead to the dynamic adaptation network, or DyAd. It's a model-based meta-learning method for learning dynamics. So in this, essentially, we're given multiple, so we're sampling from the space of different buoyant factors, buoyant forces. So we have data coming from different buoyant forces in the training. And then we have two types of components, two components in our model, where it has an encoder and a forecaster. So we train our model using multiple tasks, where here each task is defined as forecasting a turbulence of a particular external force or a particular constant of motion or boundary condition, and that's what we call a task. In the training, we feed the model with multiple tasks simultaneously, and then we use the encoder network to infer this hidden task parameter, and that's what we call the task inference, because it's not obvious from human eyes what exactly is the external force that is being applied to this turbulence, and hence we want the machine learning model to infer that from data, and that leads to the latent variable model here, where the latent variable z represents the hidden external force or other parameters such as boundary conditions or constant of motion. And we enforce this kind of encoder network to have time invariant symmetry. This can be done through two parts. One is that through the design of architecture, and we already talked about how we can design equivariant networks that are symmetric or equivariant with respect to a certain symmetry group. Here we're looking at time translation symmetry. And the other kind of constraint that we're implementing into this model is through the loss function. So this is a multitask training, right? And we enforce time invariant symmetry in the latent space through this time shift invariant encoder network. And then through the architecture and through the loss function, where we constrain the parameters in the latent space z of c of different tasks, where I and j stands for different tasks or different timestamp, to be the same. So this constrains latent variable to not change across different timestamps. And then we also add some addition. So this is a task parameter we use as a weak supervision to the model, because we actually don't know the external force from the data. So we can compute some surrogate to represent the task parameter. And then in our experiment, we use the average velocity as a surrogate parameter to indicate the task. So this represents some sort of weak supervision signal to help the learning of latent variables. And then these are the hidden features that we want to learn. This represents the time invariant buoyancy forces. And we also add a regularizer to avoid the yield condition situation, whereas all the z's become 0. So with the encoder network, right, we can feed the latent variable that is inferred by the encoder to the forecasting network. So in principle, you can use any forecasting network that is conditioned on the latent variables inferred by the encoder. And then in this case, we use I think we use a multi-layer CNN architecture, 2D CNN convolved over to each frames. And then we use the Z variable, the latent variable, to adapt the forecasting network. And this part is the adaptation network. And with adaptation, right, for the different tasks, the model is able to forecast for turbulence of completely different characteristics. And note that in the testing, this turbulence is sampled outside of the regime of the training tasks. So this is talking about like extreme generalization, not outside of the group transformation. So in terms of adaptation, we borrow some ideas from neural style transfer literature to control how the forecasting network is going to react. So we use adaptive instant adaptation, right? This represents kind of the boundary condition. It's represent the external force factors in the turbulence. So we basically normalize the coefficients and external forces by normalize each instance, subtract the mean and divide by the standard deviation per instance. And we use adaptive padding, AdaPad, to represent the boundary conditions in the turbulence. Essentially, we compute using a linear layer to transform the hidden features into the boundaries. And then we pad these boundaries around the predicted velocity field, and this is adaptive padding. So we pad the boundary conditions outside of the spatial domain. So we intertwine the adaptive instant normalization and adaptive padding in our forecasting network that allows the forecasting network to exploit the features in Z and the latent features and adapt to changing dynamics. Okay, then we also proved in our paper that this way of doing multitask training and adaptation can indeed improve generalization. So this is a typical generalization bound that you will see in learning theory. But we generalize the classic results from ENDO 2005, which shows that the multitask, we're looking at individual tasks, generalization bounds for task mu1 to mu_k. But in our case, we're essentially looking at multitask training, right? But then domain adaptation during forecasting. So we can show that this multitask learning framework indeed has generalization better than learning each task independently. And this kind of shared data during training tightens the generalization bound. And in terms of generalization for inference, we basically need to look at the domain distributional difference measured by Wasserstein distance. And that's like a proposition in our paper that I will not describe in detail. So in terms of performance, we can look at many different meta-learning frameworks. For example, MAML, right, is an optimization-based meta-learning framework. MetaNet is another model-based meta-learning method. And there are other type of meta-learning methods, such as modular-based individual modules, where you combine modules through attention. So these are all model-based meta-learning framework. And we look at different data sets. So turbulent flow is for forecasting the ocean turbulence. And sea temperature is also another type of data, a benchmark data set for spatial temporal forecasting, and then the ocean currents. So we're looking at two meta-learning scenarios, right? One is meta-learning into the future. So in this case, we need to deal with dynamics with different initial condition, because the dynamics is not stationary. So when we are training our model in the past dynamics and looking at the future dynamics, the initial condition of the dynamics have changed from training to testing. So that's what we call the test future meta-learning scenario. A second scenario is test domain, which means the data actually have different external forces. So we train our model on a set of parameters in external forces, and then we test our model on a completely different external forces. So we measure the prediction performance for RMSE and the energy spectrum error as similar as before. Note that in this case, we have relaxed our test situation, the generalization scenario, where we're looking at transformations or changes in distribution outside of the group transformation. Okay, so we can see that our model DyAd, right, with different forecasting network actually is indifferent with the forecasting network we use, as long as you use the adaptation scheme with time invariant features. So you can see that the performance is superior across all the data sets, right, with standard deviation. And most importantly, we want to know that the optimization-based meta-learning framework, such as MML, actually doesn't work well for this kind of task, continuous valued forecasting task. We hypothesize that it's because one, it requires the tasks during testing time to perform meta-gradient updates, which is tricky for continuous tasks where we have continuous values in output space. Two is it's actually quite slow to perform meta-gradient updates in our tasks. So optimization also poses additional challenge for MML. I can also show you the prediction viralization for our model. So we're looking at two different external forces, where forces equal 9, which means the turbulence is less turbulent, and the fluid flow is less turbulent. And then when the force is equal 21, the fluid flow is much more turbulent. So the fifth column is the ground truth, and the DyAd prediction modular weighted is a baseline with model-based meta-learning methods, and ResNet is a generic multitask learning. So we just train the model with all the tasks together and hope the model can learn underlying dynamics, but it actually doesn't learn. So if we look at, for example, the predicted turbulence of our model, we can see that DyAd can accurately capture the small scale dynamics in the target, whereas modular weighted meta-learning method has some artifacts, right? When the fluid starts to rotate, and ResNet does predict something, but the large scale behavior is relatively correct, but the small scale dynamics is lost in this case. And then if we test on a much more turbulent cases where the fluid becomes much more violent, again, DyAd can capture relatively well this dynamics and its turbulence, but modular weight again has some artifacts. ResNet is generating very blurry predictions. Okay, so, and I also want to highlight that this type of two instances of turbulence has never been seen in the training set. So this is out of sample distribution in terms of dynamics. Okay, to conclude, hopefully I have, help you understand a little bit better about generalization problems in learning, especially for dynamics learning, which is slightly different from the traditional generalization, notion of generalization in typical machine learning tasks. And we talked about one approach that we can potentially use to resolve generalization issue, that is the idea of using symmetry. And we want to incorporate symmetries for learning complex dynamics. And I talked about equivariant networks, which is to explore symmetries in differential equations and add that to neural networks and design symmetry-aware equivariant networks. And then I talked about ECHO, which is a type of rotational equivariant networks applied to multi-agent trajectories for real-world trajectory forecasting. And then I also mentioned DyAd, which is way to incorporate symmetry in the hidden features, and then use the hidden features to adapt the predictors for various situations. So with that, I want to just thank, you can check out the code and the data on my website or follow me on Twitter. And I want to thank all the funding agencies for supporting our work. Thank you.
Thank you so much, Professor Yu. Could we all unmute ourselves and thank Professor Yu?
Oh, thanks.
Thank you.
Okay, so yeah, so we have some time for questions. So if anyone has a question, feel free to raise your hand or just unmute yourself and ask the question. Okay, so Professor Barto.
Yes, hi. So very nice talk.
Thank you.
I have, I'm just thinking about convolutional neural networks were inspired by the visual system and the brain. And I'm wondering if the other kinds of symmetries that you have incorporated into networks, have you thought about what they might tell us about real neural networks?
Oh, that's a great question. Yeah, I don't know, because I'm not an expert in neuroscience, right? I mean, when I talk about equivariant continuous convolution for traffic, I use the example of how we make decisions regardless of orientation or intersections. But that's only a hypothesis. We don't know how to test it. Perhaps I can I don't know, if you have good pointers or people who have more insights, I'd love to talk with them.
Thank you. Very nice work. Thank you.
Thank you.
Okay, Ivan?
Yes. Hello, Professor. Thank you for the talk.
Hi.
I had a question concerning the symmetry and its relation to non-equilibrium systems. So if these the generalizability comes from the symmetry relations, and the symmetry relations are originated from conservation laws or have an associated conservation law, right? What happens when trying to model non-equilibrium systems utilizing the symmetries as
Right, then I see. Yeah, I mean, that's a great question. So we have thought about this, right? So this is a sufficient condition saying that, every symmetry, there's a conservation law, but it doesn't mean non-conserved system does not have symmetry,
Okay.
right? So one thing we are really interested to study is imperfect symmetries, because real data always have imperfect symmetry or partial symmetry, right? That's one thing we try to study in the third work of DyAd, which is saying that maybe there's no symmetry in the data space, but there are hidden symmetry in the latent space, and we can exploit that in some way. So yeah, but back to your question, I think that's a perfectly valid point, and we'd love to understand a bit more. We also want reason we want NSF award to study is a mathematical foundation of symmetry in deep learning. So we're looking for great people to join us.
So, so you're basically saying that what you did with DyAd is basically there are a bunch of local symmetries that you can exploit if there's no global symmetry that can be exploited.
The DyAd place is saying that there may not be obvious symmetry in the data space, but there is some symmetry in the latent space, and you can correctly infer the latent variables and then enforce symmetry in the latent space. We can also have some performance gain.
Okay, so sorry. I'm very new to machine learning.
It's okay.
Yeah, my work is in computational electronic structure, so I'm very new to. So what do you mean by the latent space versus the domain space? Or
right. So yeah. So in our case, in the example of turbulence, right? What we see is the velocity field. That's the data space, right? We do see them. But then the external force is something that's hidden. because, right, so that's what I mean by latent space. But in a generic sense, I guess in the machine learning case, we often talk about latent variables, which represent, I don't know, for different users, you have different preferences for movies, and user group preferences is a hidden variable that we model.
Okay, so it's just something that needs to be inferred.
Yes.
Okay, okay. Thank you, Professor.
No problem.
Okay, Professor Moss.
Yes, thank you. I enjoyed the talk a lot.
Thank you.
So my question has to do, I work with time series data around computer systems, actually. So it's not obvious whether physical models work or not, but setting that aside for the moment. Imagine a case like I want to predict the amount of storage a compiler is going to demand as it goes along. And as it compiles each function, you get a kind of shape to the use of the storage. When it's done, it's going to release most of it. But depending on the size of the function, you're going to get a bigger instance of the same shape. So it's going to be stretched in time and in your one sort of spatial dimension, or just the height. So it's not really spatial data, but that's why I was asking the thing about, so there's a self-similarity, but you've got different scales in the same problem. Any idea how to design networks that would exploit that or figure it out?
Right, I think, yeah, I mean, if you have this kind of like scale in time, right, this is a special instance of what we mean by scale symmetry. Because scales can happen both in space and time, like the velocity field we showed is on space, but you can just reduce that to one dimension. That would be like a scaling in time. And you can still design scale equivariant networks to make predictions at different time scales, right? And people actually have done that. Like, for example, you can use sort of variations of convolutional neural network, like temporal convolution, to model time series, right, at different scale. People also construct hierarchical models where each model is modeling the dynamics of particular time scale, but then compose them. And obviously that kind of approach is very like parameter inefficient, because you have to stack multiple neural networks on top of each other. But we think designing equivariant networks can hopefully reduce the number of parameters you need, right? Because it can exploit the symmetries in the data. And also I want to know that all the examples I talked about, some of them are motivated from physical systems, but the model itself does not use the equation itself, right? For like compiler dynamics, or we also use similar line of models for pandemic modeling, that we don't even know the equations that governs the pandemic, because it's too complicated to write it down. So our models, they're motivated by equations, but they're not using any of the equations. So we think they should probably be applicable to cases where we cannot write down the equations that governs the dynamics.
Yeah, I was pondering your thing with the traffic movement of vehicles and other entities in traffic, and thinking, well, what are some of the things that would undermine that rotational symmetry? So one would be where a secondary road intersects a primary road. So you're going to have different behaviors in the two directions. Or even the compass direction might affect things if you've got sunlight in people's eyes at a particular time of day or something like that, where obviously the human behavior is going to be a little different. But I would think that it could probably even learn that sort of thing. It's an imperfect symmetry, but there's still, as you say, a lot of symmetry, a lot of similarity of behavior. Put another way, an individual driver coming in any particular direction is probably going to behave pretty similarly to other drivers coming in that direction.
That's the intuition we use.
There's some variation there, but I might behave differently coming in, on the primary road versus the secondary road. But anyway, a really cool problem to work on. Thanks.
Thank you. Great comments.
Okay, do we have any more questions? We have a
There's
bit more
something
time.
on the chat. Oh wait, it's a
Oh, just
wait.
yeah, just fantastic talk.
Oh.
Excuse me, can you explain the continuous convolutions a little bit more? I'm not familiar with them.
Oh yeah, so it's just a fancy name of doing like graph convolution. so the typical, okay, I think I might have like a backup slide. Let's see. Do I have a backup slide? Okay, great. Okay, so this is the backup slide for like continuous convolution. So okay, so when we talk about discrete convolution, this is a picture from one of our earlier papers of doing like discrete convolution on a graph, right? So a graph in this case is the sensor network where the edges, the nodes represent different sensors, edges represent the connectivity on the road. We can abstract it as a fixed graph. And then we can do convolution on this fixed graph. And this is a discrete convolution because we're discretizing the space, right? A standard convolutional neural network is a special case of this where the underlying network is a lattice or a grid. This is a more general version of that. But a continuous convolution is saying that, well, when we do convolution, right, we're just looking at the adjacent neighborhoods and then aggregate the features according to coefficients defined by the filter, right? But then for continuous convolution, because the cars are always moving, right? So this is a LiDAR image of autonomous vehicles, and the cars are always moving. And when we do convolution, centering on a particular vehicle, the reference frame are always changing. So in continuous convolution, and therefore we have to account for that. So the underlying graph is changing over time. And so when we center a particular vehicle as the bullseye of the convolutional kernel, right, in our polar coordinates, then we have to compute the edges according to the relative position of two vehicles. So let's say we're looking at the vehicle I, right? Then we need to convolve around the neighboring particles, J's, where J's belong to, you know, all the particles that falls inside this red circle. And then for every pair, xi and xj, we compare their relative positions, which is time dependent, by the way. And then we do the same thing for this like outer map, right? So the kernel itself is time dependent, which means that the underlying graph is changing, you know, in a continuous space. So that's why it gets the name continuous convolution. It's a special type of graph convolution where you convolve along this graph. Does that answer your question?
Yes, thanks.
Mm-hmm.
Okay, so we're mostly out of time. Does anyone have one final question? Okay, let's all unmute ourselves and thank Professor Yu once again.
Thank you guys. You guys are
Thanks.
awesome.
Thank you, Professor.
Yeah, take care.
Okay,
Bye.
so I'll just stop the recording.